What's up, everybody? My name is Eric. Welcome to my channel, Eric the Tutor. Today, we're going to be talking about carbohydrate classification, and we're going to examine the various types of carbohydrates we utilize for metabolism and the structures in which they exist. The following video, we're going to look at the biochemical reactions they undergo. Alright, so let's go ahead and jump into it. From a molecular standpoint, carbohydrates used to be defined by C sub X, H2O sub X. If we examine the word carbohydrate, we have carbo for carbon and hydrate for water. But this definition is now considered outdated, this C sub X, H2O sub X. This formula only applies to single monomeric sugars, such as monosaccharides. As simple sugars link to form complex sugars, water loss is going to occur. So if we lose water, that's going to be a dehydration reaction. Dehydration. So instead of using this C sub X, H2O sub X, we're actually going to use C sub X, H2O sub Y. Let's go ahead and look at monosaccharides in greater detail. So let's go ahead and go to the next slide. So whenever we discuss carbohydrates, it makes sense to start with the most basic structural units. The simplest monosaccharides contain 3 carbon atoms, and they're called trioses. So I can put up here trioses. Now we can see we have a carbon here, a second carbon there, and a third carbon there. So these are all trioses. Now, do you see something that's a little bit different about these molecules? This molecule up here and this molecule down here. Well, the molecule on the top has a functional group that we can recognize as an aldehyde. And down here, the functional group is a ketone. So what do you think these would be called? This will be called an aldose. And this one could be called a ketose. So we can have aldoses and ketoses, and then we could also have trioses, pentoses, and hexoses, which we will examine in the following slide. So let's go ahead and look at a hexose. We're going to look at D-glucose. So this is a type of hexose. Now, typically, we've been working with dash and wedges. I'm going to introduce a new way of analyzing the carbons that makes it easier for us to write them down. And it's what Dr. Emil Fischer founded when he was working with carbohydrates. So I'm going to go ahead and draw a bow tie structure. As I previously mentioned, a Fischer projection is a way of drawing sugars and showing the carbon chain as vertical, as we can see along this vertical spine here. And the horizontal groups are wedged and they're coming out of the board. Now if we actually smush this molecule flat, this will give us our Fischer projection. Stereochemistry can be applied to our Fischer projections as we label our highest priority to lowest priority groups. The OH being highest priority. Coming off of this carbon, we have priority number 2 with the aldehyde, and the rest of the carbon chain would be number 3, and our hydrogen will be number 4. So at this moment, it appears that our stereochem is S. However, we recognize that the hydrogen is coming out of the board, so we have to flip our stereochem to give us an R configuration. We can do this for the rest of the molecules. We label number 1, 2, 3, and 4. This appears to be R, but it's actually S. A little trick is whenever the OH is going to be on the right side of the group, we know that it's going to give us an R configuration every time. So this will be an R, this will be an R. And if the OH is on the left, then it's going to give us an S configuration. Let's go ahead and examine common names that are frequently tested on exams. These sugars are by far the most popular. We have D-fructose, D-glucose, D-galactose, and D-mannose. So these structures would be important to memorize. Now, you're probably wondering, what is this D we speak of? Well, while organic chemists tend to use the newer RNS systems where we can label each stereo center as R, R, S, R, and R, we could do that for all of the molecules. Biochemists tend to use the older DNL system in which the chiral center furthest away from the carbonyl. So that would be all of these guys here will determine if it's going to be D or L, where D represents the highest functional group being on the right. So you can see all of these are on the right. So these would give us D. Now you can imagine if we had something such as, say we had a glyceraldehyde and we had a OH group. Do you think this would be a D or an L? Well, this stereocenter is the furthest away from the carbonyl, and we see that our OH group, our highest priority group, is on the right. So this is going to give us a D configuration. But if we drew the mirror image of glyceraldehyde, now our highest priority group is going to be on the left. So what do you think this would be called? Is this still going to be D? This is going to be called L-glyceraldehyde. L-glyceraldehyde. D-glyceraldehyde was later determined to exhibit a positive rotation. While the L-glyceraldehyde was found to have a negative rotation. So we have L and we have a negative rotation. It is important to note, however, that the direction of the rotation, whether that be positive or negative, must be determined experimentally and cannot be determined from the D or L designation of the sugar. Let us now examine in more detail R and S and D and L configurations and also bring up the importance of stereoisomers. We can see here we have 4 novel molecules. So go ahead and pause the video and label whether it's going to be D or L and whether each chiral center is going to have an R or S configuration. Well, we see here that our OH is on the left, so we can assign an S configuration for the stereochemistry. Same goes here. We also see that our OH is furthest away from the carbonyl. Our stereocenter that's furthest away from the carbonyl is on the left. So we know this is going to be an L. Let's go ahead and make an adjustment here. So this should be a hydrogen here, a hydrogen there with an OH here and an OH here. Now, we're going to go ahead and assign the stereochem for this. So the OH is on the right. So we know this is going to be an R configuration. Same thing here. And our highest priority group that has a stereo center furthest away from the carbonyl is on our right. So we know this is going to be a D sugar. And over here we have OH on the right, OH on the left. So we can go ahead and do R, and we can do S. Here is an S, and there is an R. Furthest priority group from the carbonyl is on the left, is going to give us an L. And furthest priority group from the carbonyl is on the right. This is going to give us a D. Now, what type of relationship do these molecules have with one another? Well, let's go ahead and examine them. These two are mirror images of each other. They are non-superimposable images of each other. So that means, let's go ahead and label this A, B, C, and D. A and B are going to be enantiomers. That is non-superimposable mirror images. And we can also see that C and D will be enantiomers of each other. Now we can introduce a new term, and this new term is a diastereomer. diastereomer. That's when we change one of the chiral centers. We change at least one chiral center, but not all of them. Because remember, if we change all of the stereocenters, this is going to give us an enantiomer. So a diastereomer, we can change at least one. At least one stereocenter, but not all. So which of these would be diastereomers to each other? Well, we see here the OH group stays the same here. But our OH is on the left side here, and our OH group is on the right side. So we can say A and D are diastereomers. And then what about the middle group here? So our middle group, our OH group, stays the same, but our OHs here have switched at this chiral center. So we also know that B and C are diastereomers. Now the last term I want to introduce is an epimer. Epimer. This is when we change a chiral center at exactly one, change chiral center at exactly one location. One location. So in this case, epimers are a subtype of diastereomers, where A and D in this case are also epimers, and B and C are epimers. Now you can imagine we have a longer molecule, and we're going to have many different chiral centers changing. So it's important to recognize if only one of those chiral centers changes, then it's going to be known as an epimer. If we have multiple chiral centers changing, then we can't call it an epimer, but we can call it a diastereomer. Now I also want to point out, if we look at A and C, A and C, we go from an S configuration to an R, and we have an S configuration to an S. So the S configuration there and the furthest stereocenter stay the same, but we changed at least one chiral center. So A and C would also be diastereomers. Now let's go ahead and look at B and D. B and D, we notice that this chiral center stayed the same. Both are. And up here we went from R to an S. So again, we have B and D equal diastereomers because we're changing at least one chiral center. They can also be called epimers. So B and D and A and C, same with A and D and B and C, they can also be called epimers in this example because we're changing the chiral center at exactly one location. Now again, you can imagine we have a longer chain. If we have multiple chiral centers changing, it will not be called an epimer in that case. Thanks for tuning in, guys. The next video we produce, we're going to be examining the biochemical reactions that these molecules undergo.